Welcome to the advanced power electronics and control courses. Today, we shall discuss today single phase converter. Single phase converter finds its applications wide application because previously we had a DC supply and thus we had a DC loads. Once the supply has been changed to the AC, then we require a genuine purpose to rectify this. For example, actually in the older household in Calcutta which already had a DC supply, we require to rectify it to put it to the actually DC fans, any other applications. So, now we refer to the process of conversion to the AC to DC as rectifications. So, rectification refer to the process of converting an AC voltage and current to the DC voltage and current. And rectification specially referred to the power electronics converter, where the power flows from AC side to the DC side and not the generative way. Mostly AC will be the source and load will be the DC, and mostly these are DC motors. Now, point of interest of the analysis of the rectifier will be actually we require to analysis the waveform of the while AC to DC conversion. So, while various things, but input side when you talk about the waveforms and characteristics values, when you talk about DC value after rectification we will have a average value and we will have a RMS value because we have a ripple DC, not a constant DC with a rectified voltage at the current. Then due to rectification there is influence of the load and the rectified voltage and the current will change according to the type of load, whether it is RL, RLE, different kind of load will give us a different kind of waveform. Harmonic content in the input. So, you are feeding AC. So, since it is a nonlinear conversions, AC to DC conversion then leads to the harmonic contamination in the source side. So, we will see that what is the problem or what is the cause of the arising the harmonics in the input. Voltage and current ratings of the power electronic device used for the rectifier operation that also be analyzed. So, what should be the proper rating for the particular wattage of the load. Reactions of the rectifier circuit upon the AC networks, reactive power equipments and the power factor harmonic, these will be the actually characteristics of this actually the rectifications and rectifier control aspects. For control rectifier generally it is been achieved by the thyristors. Now, in the analysis following simplifying assumptions will be made. Internal impedance of the AC source is 0 if otherwise not mentioned or taken into the consideration. Power electronics device used in rectifications are the ideal switches. So, types of the rectifiers, we have a single phase and a 3 phase. Today we shall consider the single phase and definitely we have uncontrolled fitted by the diode based rectifier. You have a half controlled fitted by the combinations of the thyristors and the diode. They are full control, it is fed through actually the thyristors. Then we may have a half wave where we require to buck down the voltage a lot. Then we have a full wave where we require to have a total cycle. Then we have a different kind of supply, whether you have actually the midpoint of the transformer is available or not, that is also a matter of questions. If it is available then we will go for the split supply and otherwise we have a bridge kind of configurations. And same way in 3 phase also we have uncontrolled fed by the diode based rectifier, we have a half control and the full control. In uncontrolled we have a half wave as well as a full bridge, and same way we have a full control, we have a half wave and full bridge. So, all those topology will be discussed. First we will take out actually a single phase. So, let F be the instantaneous value of the any voltage and current associated with the rectifier circuit, then following terms characterizing the property of F can be defined. The peak value of F, as the name suggests, F equal to mod F max for all the time. Similarly, average DC value, that is F suffix AV, assume F to be periodic over the time period t, and so f a b will be actually you have 1 by t 0 to t f of dt, and if it is RMS effective, then f will be periodic over the same thing, and the expression of the RMS will be under root 2 1 by t 0 to t f square dt. Similarly, we will define the term form factor as f defined by f of f, f RMS by f average. Similarly, we will define the ripple factor, that is basically form factor is a ratio of basically the RMS is associated with the AC and average is associated with the DC. Since in any periodic functions, if it is a bipolar in nature, average value comes out to be 0. So, for this reason, so form factor is basically a says that the ratio of actually AC versus DC. And another aspect is the ripple factor. Ripple factor is given by FRF. So, if I put I, then it is for current ripple. If I put voltage, for the voltage ripple, that is F RMS square minus F E square by FAB. So, ultimately it comes out to be the basically the form factor square minus 1, and fundamental component F1. Since it is contaminated with the harmonics, the input side we wanted to know what is the fundamental value of the fundamental component. In our case, it will what will be the 50 hertz component of it. Its RMS value of the sinusoidal component in the Fourier series expressions of f will be frequency 1 by t, because you have a sine and cos component. So, so it will be f a 1 square plus f b square. Similarly, we can calculate the term f a 1 and f b 1, these are basically the Fourier components. So, one the same way we have find it out the Fourier series coefficients, same way we can do it. So, it is 2 by t 0 to t f t cos 2 pi by t dt, and similarly for f b 1 you will have a, instead of cos you have a sine term. Now, for kth harmonic, if I wish to know, because there is a symmetry, generally different kind of harmonics are present for the different kind of system. Sometime actually triplet harmonic is absent, sometime actually we have a harmonic content maybe the 6n plus minus 1, that is fast 5th and 7th, thereafter 11, 13 and so on. So, if you wish to calculate the kth harmonic component of this Fk, it is the RMS value of the sinusoidal component of the Fourier series expressions of f with a frequency k by t. So, Fk equal to under root of half f ak square plus half bk square. So, from there we can calculate the result f ak equal to 2 by t 0 to t f t cos 2 pi k t by t dt. Similarly, you can have the sine term, that is basically 2 by t 0 to t f t sine term. So, there will be a definition called crest factor. Crest factor is by definition is caret f by f RMS, that is a peak value by RMS. Similarly, we will have a distortion factor. Distortion factor is given by basically by definition it will be f1, that is a fundamental component, by RMS will give you the distortion factor. And another is actually total harmonic distortion. This is a very important classifier. We want that actually now IEEE practices says THD of the input current or anything required to be a specified limit. The amount of the distortion in the waveform f is quantified by means of the index. Total harmonic distortion is given by THD equal to under root of actually k equal to 0 to infinity fk by f1 square, and from there actually we can derive, students are requested to refer to the any standard book and the derivations are been there. So, we can find it out the THD equal to under root of 1 minus df square by df. So, these are few terms we can use very frequently while analyzing the single phase and the 3-phase converter. Another is the displacement power factor of the rectifier, that is DPF. Let us say if Vi are in a phase, then amount of the voltage and current of the rectifier are actually phase shifted. Then the displacement power factor of the rectifier is defined as, that is cos phi 1, where phi 1 is the phase angle between the fundamental component and current and the voltages. Let us understand what does it mean by this. So, let us consider that actually this is the sinusoidal voltage and you are triggering a thyristor. So, it will be delayed by an angle alpha. So, current will start conducting from here. So, there will be a delay. So, this delay corresponds to alpha, and that if you say that it is phi, then let us go back and let's understand this definition. If Vi and the I are the phase input voltages and current of a rectifier respectively or converter, then displacement factor of the rectifier / converter is defined as dPf equal to cos phi I is the phase angle between the fundamental component of the Vi and Ii. So, we assume that voltage only have a fundamental and it has lot of harmonics. So, if you actually whatever its fundamental phase difference with the fundamental voltage, that will be actually defined as dPf. Power factor of the rectifier. So, as for any equipment, the definition of the power factor of a rectifier is the actual power factor of the rectifier upon the apparent input of the rectifier. That means, if the phase input voltage and current of the rectifier Vi and Ii respectively, then actually power factor will be given by Vi1 of fundamental I1, that is a fundamental, into cos phi of I of the input power factor angle between the fundamental of voltage and current, which we have calculated here, by IRMS and the VRMS. So, this will be the power factor in the rectification. These term will be used, and while used will be, and assignment will be given to calculate those terms. If the rectifier is supplied from an ideal sinusoidal voltage source, then as I have drawn little bit ago, that is Vi1 and V fundamentals become same. Thus, the PF power factor will be II1 by IRMS into cos phi I, that is basically dPf 1 into dPf. So, we can replace then in terms of the we can replace them in terms of the THD. So, power factor will be dPf by under root 1 plus THD square. Another important parameters of analyzing the rectifier and the converter is that pulse number of a rectifier refer to the number of the output voltage current, whatever parameter you are analyzing, whether output voltage or current, pulse in a single time period in the input AC supply. Mathematically, the pulse number of the rectifier is given by the time period of the input voltage supply by time period of the minimum order harmonic in the output voltage or current. So, that required to be little understood. So, it depends only mainly the 3-phase supply. So, there we can see the different kind of pulses, how many number of pulses will be generating. So, classification of the rectifier can also be done in terms of the pulse number, and for this reason we have a different kind of pulse converter. In 3-phase we say that it is 6 pulse converter, because what happened, we will discuss in detail while discussing the actually the 3-phase circuit. If it is uncontrolled one pair of thyristors or diode or combination of the thyristor diode in case of the semi controlled, will convert for the period of 60 degree. So, you have a total actually 360 degree. So, you got a 6 such pulses. So, for this reason classification of the rectifier can also be done in terms of their pulse number. Similarly, we can have actually a phase shifted by 30 degree and we can by a transformer and we can have a 12 pulse. Similarly, we have a 24 pulse, similarly we may have a 48 pulse and we shall see the utility of it while reduction of the harmonic and the other characteristics that has been required. Commutation in a rectifier. Rectifier to process the transfer of current from one device to the another device, mostly it is diode or thyristors, to the other rectifier, the device from which current is transferred to the other transfer is called the outgoing device and the device to which the current is transferred it is called the incoming device. The incoming device turn on at the beginning of the commutation, while the outgoing device turns off at the end of the commutation. So, we have a sometime there is a overlap, we will come across it and we will see that what is the cause of the overlapping also. Commutation failure. It refers to the situation where outgoing devices fails to turn off at the end of the commutations and continues to conduct current, and that is dangerous. Say you have a thyristor legs. So, you may actually some thyristors is going out and some thyristor comes in. Generally, if you have even it may leads to the shorting of the legs. So, that is quite dangerous phenomena. Firing angle of a rectifier, that is alpha, we have discussed in detail in the thyristors. So, it is the angle by which the conduction of the thyristors is delayed and it is measured from the instant when device is becoming forward biased with the resistive load. Therefore, the reference point should be a fixed point. So, for the single phase it is a forward zero crossing and it is a for the 3 phase the place where actually this VC and VA cross. So, that place is considered as a firing reference. We can start calculating firing reference from that point for the 3 phase, but today our discussion will be mainly on the single phase. Extinction angle of the rectifier or converter. It is also used in connections with the control rectifier, refers to the time interval from the instant when the current through the outgoing thyristors becomes 0 and the negative voltage is applied across it to the instant when positive voltage is applied. So, within that time actually that is said to be the extinction angle of the converter or rectifier. Overlapping angle, that is called mu. It arises though we have if we have a contradiction with our first assumption. We have assumed that actually source does not have an impedance. It comes into the pictures when source got an inductance. Commutation process in a practical rectifier is not instantaneous. During the period of commutation, both incoming and the outgoing devices conduct current simultaneously for a small period of time. This period is expressed in radians, all angles are expressed in radians and is called the overlapping angle of the rectifier, and easily verified that alpha plus mu plus this actually the extinction angle, that should be equal to that total half cycle of the period, that is pi. And generally this mu will be larger if there is a huge source inductance. Now, let us come to the first simplest circuit configuration, that is single phase uncontrolled converter, half wave diode rectifier feeding a resistive load. So, what happened here actually diode has to block the peak reverse voltage. So, what happen when it is conduct? So, it has to be block the peak reverse voltage, and this is basically the voltage across the load, and this is the voltage across the diode. Now, for the simplest circuit, let us calculate the parameter. Now, we can calculate this parameter, that is actually the average value of the voltage which we have shown there. So, it is 1 by pi 0 to pi and so on. So, you get Vm by pi for the half wave for the single phase uncontrolled. Average output load current, you divide it, just it by R, you will get this value Vm by pi R. RMS value, you will get Vm by 2. RMS of the load current, definitely Vrms by R, you get it, and the peak inverse voltage across the diode will be Vm, that is what you have seen in the previous slide, and the efficiency of the rectifier is PDC by PSC. So, that will VDC into IDC, Vrms into IRMS, and you can calculate what should be its value. Similarly, effective RMS value of the AC component will be VAC, Vrms square minus VDC square. So, VDC is quite actually small, for this reason actually there is a considerable amount of the AC inside it. The form factor, it is Vrms by VDC, that is also high, and also ripple factor is VAC by VDC, you can form it, that is form factor square minus 1, that will be a ripple factor, that also will be quite high. Now, single phase uncontrolled converter, total harmonic, the harmonic factor or the total harmonic distortion, that is one important parameter for the current or the power quality. Measures of the distortion of the waveform from the input current, that is THD equal to IH by ISM1, that is IS square minus IS1 square by S1, ultimately you will get this value. Essentially, if it is a very high inductive load, then input current will get this form, otherwise it will be Vm by R. So, that will be different. So, this will be applicable when actually R is much less than basically XL. Generally, if R by XL, this ratio is actually around 0.1, then we can say that load current through this load almost constant, and the input current will have this kind of profile, and there we are coming into the analysis, let us say, and ultimately this is your fundamental of the input current ISO1, and this is your input current. So, from there you can calculate the value of the other parameter, that is df cos phi and the power factor and other parameter also. Now, let us consider a single phase uncontrolled rectifier RL load with the free fill. We have seen a different kind of topologies of the converter in our previous class with SPST switches. So, you got a diode and thereafter you got a VL and VR. So, what happened, due to inductive load, the conduction period of the diode D1 will extend beyond 180 degree, because current will still continue to after 180 degree until the current becomes 0. So, this is the point where actually current becomes 0. This is the point where diode D1 conducts if this thing is absent. Now, what happens if it is actually closed or it has been put into the circuit? Then what will happen? Then there will be a change in the circuit. So, this is a Vm and ultimately it will conduct till this time, Thereafter, there will be no negative voltage associated with it, because output voltage will come like this and till actually the angle beta, and this is actually the VR. VR will be basically the voltages across this, actually the resistance of the load. VL is the voltage across the inductor. So, you can see that change in the polarities takes place. This is basically the VD ultimately when it conducts. So, it is, we assume that actually forward voltage drop of this device is almost negligible and equal to 0. Then it is blocking these voltages of maximum Vm and thus continues. So, this is actually the RL load. Now, what will be the average value of the output voltage here? So, we can calculate, you see that how it will change. So, VDC will be actually Vm by 2 pi 1 minus cos pi plus theta, where theta can be calculated, basically that depends on basically this omega L by R ratio, and where omega is the supply frequency of the source, and from there actually you can calculate the amount of the VDC will come actually as an average value. An average value of the current definitely once you calculate, because the inductor does not contribute anything, once you calculate the VDC divided by R, you will get IDC. So, average value of the output voltage and hence the current can be increased by making theta equal to 0. So, that this value becomes basically -1 or -1 2. So, you approaches to the resistive load, that is Vm by pi, which is possible adding a free wheel diode Dm across the load. So, what does it do? This diode with rectifier, if you put a free wheel diode, will increase your average DC value available to the load. So, this is a one utility of it. So, for this reason we prefer to have free wheel action in a AC to DC conversion kind of applications. So, single phase uncontrolled converter with RL load with a freewheeling diode we are actually discussing. So, effect of the freewheel diode DM is to prevent the negative voltage appearing. Once this negative voltage appearing means actually it makes it more DC or more ripple. Negative voltage appears across the load, and as a result magnetic energy stored into the system increases at T equal to pi by omega. The current D1 transform to DM and its process called commutations of the diode. So, you take an example of it. So, this is basically the Vm and this is basically the VR, and this is the point where actually D1 conducts, and this is the point where actually assuming that very high load current, then only it happens, otherwise we will have a discontinuous mode of conductions. So, thank you for your attention. We shall continue to discuss AC to DC conversion in our next class. Thank you.